Hi, welcome to my class in spherical trigonometry. Both the plane trigonometry and spherical trigonometry are concerned with the study and measurements of triangles. But what are the differences and similarities between plane trigonometry and spherical trigonometry? In plane trigonometry, we deal with triangles on a plane, such as this triangle, or triangles drawn in the Cartesian plane, such as this triangle. In spherical trigonometry, we deal with triangles on a sphere, such as this triangle. And this triangle on a sphere is referred to as a spherical triangle, or also known as the curved triangle. In a plane triangle, the vertices of the triangle are denoted by capital letters of the English alphabet. And these capital letters also denote the angles of a triangle. Such as in this triangle in the Cartesian plane, this vertex is vertex A, and this A also denotes the angle at vertex A. And this vertex is denoted by capital letter B, and capital letter D also denotes the angle at this vertex. And the angle at this vertex is denoted by C, or we say that this angle is angle C. In spherical triangle, the vertices of spherical triangle are also denoted by capital letters of the English alphabet. So this is vertex A, vertex B, and vertex C of this spherical triangle. The shaded part of this diagram is the spherical triangle with vertices A, B, and C. In plane trigonometry, the three sides of a plane triangle are denoted by small letters of the English alphabet. The side opposite angle A is this line segment through the vertices B and C, whose length is small a. Or we simply say small a is the side opposite angle A. In this plane triangle in the Cartesian plane, the side opposite angle B is the side through the line segment through the vertices A and C of this triangle. And its length is denoted by small b. Or we simply say small b is the side opposite angle B. And here the angle C is the angle at this vertex, and its side is the line segment through the vertices A and B, whose length is small c. Or we simply say small c is the side opposite angle C. In the same way, the sides opposite the vertices in spherical triangle are denoted by small letters of the English alphabet. In this spherical triangle with vertices A, B, and C, the three sides of the spherical triangle, the triangle on a sphere, are denoted by small letters of the English alphabet. So small a is the side through the vertices B and C, and small a is the side of the spherical triangle opposite vertex A. Small b is the side through the vertices A and C. It is the side opposite vertex B. And small letter C is the side opposite. C is the side opposite the vertices A and B. And small c is the side opposite angle C. In this spherical triangle with vertices A, B, C, the angles at each vertex is denoted by a Greek letter. Hence, the angle at vertex A, this angle, is denoted by alpha. The angle at vertex B, this angle is denoted by the Greek letter beta. And the angle at vertex C is denoted by this Greek letter gamma. Whether we study the triangle in plane trigonometry or the triangles in spherical trigonometry, a triangle has always 6 parts. And these 6 parts are the 3 sides and the 3 angles. In this triangle, the 3 angles are angle A, angle B, angle C. And the 3 sides are denoted by small letters A, B, and C. In this spherical triangle, the 3 angles are denoted by the Greek letters alpha, the angle at vertex A, beta, the angle at vertex B, gamma, the angle at vertex C. And the 3 sides opposite each vertex are denoted by small letters of the English alphabet. In plane trigonometry, the sides are line segments. A triangle in plane trigonometry is bounded by line segments. For instance, this triangle ABC, the sides are the line segments BC, the line segment AB, the line segment AC. But in spherical triangle, the sides of a spherical, in spherical trigonometry, the sides of a spherical triangle are not line segments. The sides of a spherical triangle are arcs of great circles on a sphere. That is, the sides, the spherical triangle is bounded by 3 great circle arcs on a sphere. But what is a great circle? A great circle is the intersection of a plane that passes through the center of the sphere and the sphere. Again, a great circle is the intersection of the sphere and a plane that passes through the sphere, a plane that passes through the center of the sphere. And the intersection of this plane and the sphere is a circle. And the center of this circle coincides with the center of the sphere. That is, if you will pass a plane through a sphere, and the plane will pass through the center of the sphere, the intersection of this plane and the sphere is a circle, whose center is at the center of the sphere. And this circle is what is called as great circle. Consider the following examples. This is a sphere with center at this point, and the radius of the sphere is R, capital letter R. We pass a plane vertically through the sphere, and the plane P passes through the center of the sphere. The intersection of this plane P and the sphere is a circle. The center of the circle is also the center of the sphere. And the radius of this circle is equal to the radius of the sphere. And this circle is what is called as the great circle. It is the intersection of the plane that passes through the sphere, and the plane passes through the center of the sphere and the sphere. The intersection of the sphere and a plane through the center of the sphere is a circle with center at the center of the sphere and with radius equal to the radius of the sphere. And this circle is what we call great circle. Here's another example of a great circle. Now the plane passes through the sphere horizontally. That is, the plane P cuts the sphere bisects the sphere into two equal parts, and the plane P passes through the center of the sphere. This is the center of the sphere, and the radius of the sphere is denoted by capital R. The intersection of the plane P and the circle, the sphere, as you can see, is a circle with center at the center of the sphere. And you can see the radius of the circle is the same as the radius of the sphere. This circle is what we call a great circle. A great circle is the intersection of the sphere and the plane that passes through the sphere, and the plane passes through the center of the sphere. Again, the intersection of the plane, if you pass a plane through the sphere and the plane passes through the center of the sphere, the plane P will intersect the sphere, and the intersection of the plane P and the sphere is a circle whose center coincides with the center of the sphere. And the radius of the circle is equal to the radius of the sphere. This circle is what we call great circle. Consider this sphere. The center of this sphere is at this point, and we pass a plane through the sphere, but this plane P does not pass through the center of the sphere. You can see that the plane P is slant. It's not passing through the center of the sphere. Nevertheless, the intersection of the plane P that does not pass through the center of the sphere and the sphere is a circle. But the center of this circle does not coincide with the center of the sphere. Or the center of this circle is not the same as the center of the sphere. And the radius of this circle is not equal to the radius of the sphere. And this circle is not a great circle. This circle is what we call a small circle. You get a small circle when the plane that pass through the center of the you get a small circle if you pass a plane through the sphere, but the plane does not pass through the center of the sphere. The intersection of that plane P that does not pass through the center of the sphere and the sphere is also a circle. But that circle is not a great circle because its center does not coincide with the center of the sphere, and its radius is not equal to the radius of the sphere. And this circle is what we call a small circle. As we said earlier, in plane trigonometry, the triangles are bounded by line segments. A line segment is a part of a line with two endpoints. A line segment has two endpoints. But in spherical trigonometry, a spherical triangle, such as this spherical triangle, with vertices A, B, and C, are not bounded by line segments. A spherical triangle are bounded by arcs of great circle, or simply great circle arcs. An arc is a part of a circle. Consider this great circle. This great circle. In this spherical triangle, this spherical triangle with vertices A, B, C is the intersection of the three great circles. And the sides of this spherical triangle with vertices A, B, C are arcs of these three great circles. The three great circles in this example are this great circle. This is the second great circle. And this is the third great circle. You can see that this side, small a, is an arc of this great circle. And this side, small b, through vertices A and C, is an arc of or part of this great circle. And this third side, small c, through the vertices A and B, is also a part of this great circle. And it is an arc of this great circle. So those are the basic differences and similarities between the triangles on a plane and triangles on a sphere. Again, in plane trigonometry, we study triangles and measurements of triangles that can be drawn in a plane or in the Cartesian plane. In spherical trigonometry, we deal with triangles on the surface of a sphere. That's why these triangles on the surface of a sphere are known as spherical triangle or curved triangle. A spherical triangle, we said, is a triangle. Is that part on the surface of a sphere formed by three great circle arcs. Again, a spherical triangle is a part on the surface of a sphere, and the spherical triangle is formed by three intersecting arcs. And these arcs are arcs of great circle. And earlier we said that a great circle is a circle whose center coincides with the center of the sphere, and whose radius is equal to the radius of the sphere. And the great circle is obtained by passing a plane through the sphere that will pass through the center of the sphere. And the intersection of this plane and the sphere is a circle with center at the center of the sphere and with radius equal to the radius of the sphere. And we call this great circle. In order to form a spherical triangle, you need three great circles. And the intersection of the arcs or parts of these three great circles is a spherical triangle, a triangle on the surface of the earth. On the surface of the sphere. Like in plane trigonometry, a plane triangle has 6 parts. A spherical triangle has also 6 parts. In plane trigonometry, the 6 parts are the 3 angles and the 3 sides. Similarly, in spherical triangle, the 6 parts are the 3 angles and the 3 sides. Consider this spherical triangle, the spherical triangle with vertices A, B, C. This triangle ABC is on the surface of the sphere. So this spherical triangle ABC is also known as a curved triangle. it is a triangle on the surface of the sphere. And the first three angles of a spherical triangle are the angles at each vertex. This vertex A of the spherical triangle ABC is the point of intersection of two arcs. This arc through vertices AB and this arc through vertices AC. And these arcs are parts of two great circles with center at the center of the sphere. At this vertex, the angle formed by the intersection of this arc and this arc is denoted by the Greek letter alpha. And this angle alpha is on the surface of the sphere. Similarly, at vertex B, we have the angle formed by the intersection of this arc AB and the arc BC. And the angle at vertex B is denoted by the Greek letter beta. And this angle beta is also on the surface of the sphere. Lastly, at vertex C, the vertex C is the intersection of the arcs through these vertices AC and the arc through vertices BC. And the angle formed by the intersection of these two arcs, the angle formed at vertex C, is denoted by this Greek letter gamma. And gamma is also on the surface of the sphere. Hence, the angles at the three vertices of the spherical triangle are also known as surface angles because they are angles on the surface of the sphere. The three other parts of spherical triangle are the sides opposite the vertices of the spherical triangle. Opposite this vertex A is this side, denoted by small a through the vertices BC. And the side opposite angle B, denoted by small b, is this arc. The length of arc through vertices AC. The side opposite angle C is denoted by C. It is the length of arc through vertices A and B. The length of these arcs, these sides A, small b, small c, the length of these arcs are given by the angles subtended by these arcs at the center of the sphere. So the length of the side B is equal to the length of this arc through the vertices AC, and the length of this arc is the measure of this angle subtended by this arc AC at the center of the sphere. Similarly, for the side opposite angle B, the side opposite angle A, this small a, the measure of this side is small a is equal to the length of this arc through the vertices B and C of the spherical triangle. And the length of this arc is given by this angle. The angle subtended by this arc is small a at the center of the sphere. The center of the sphere is denoted by 0.0. And lastly, the side opposite angle C, the side opposite vertex C, this small letter C is the length of this side C is the length of this arc through vertices A and B, and the length of this arc AB is equal to the angle subtended by this arc AB at the center of the sphere. Consider this spherical triangle. This is the center of the sphere. And the spherical triangle has vertices A, B, C, and the 6 parts. The first 3 parts of the spherical triangle are the angles at each vertex of the spherical triangle. The angle at vertex A, again vertex A is the intersection of this arc AC, a part of the great circle, and this arc, a part of another second great circle. And the angle formed by this arc at vertex A is denoted by Greek letter alpha. The second angle B is at vertex B. The second angle of the spherical triangle is at vertex B. Vertex B is the point of intersection of this arc BC and the arc AB, and these arcs are parts of 2 great circles. The angle formed by the intersection of these arcs vertex B is denoted by Greek letter beta, and the third angle at vertex C is formed by the intersection of this arc through vertices BC and the arc through vertices AC. And these arcs are parts of 2 great circles. The angle formed by the intersection of these 2 arcs at vertex C is given by Greek letter gamma. These 3 angles at the 3 vertices of the spherical triangles, angle alpha, beta, and gamma, are called surface angles of the spherical triangles. The 3 other parts are the 3 sides of the spherical triangle. Opposite vertex A is this side, the arc BC, whose length is denoted by small a. The measure of A is equal to the length of this arc through vertices BC, and the length of this arc is equal to the angle subtended by this arc BC to the center of the sphere. This angle small a is the length of this side small a. It is the length of the arc BC. The second side is the side opposite vertex B or opposite angle beta. This side small b is the length of the arc through vertices A and C. And the length of this arc is equal to the measure of the angle subtended by this arc AC to the center of the sphere, and it is given by this angle small b. This angle small b is the measure of this side small b. It is equal to the length of the arc AC. And the third and last side of the spherical triangle is small c, the side opposite the third vertex C, or the side opposite angle gamma. The measure of this side is equal to the length of this arc AB, and the length of this arc AB is equal to the angle subtended by this arc AB to the center of the sphere. It is given by this angle small letter c. The angle small letter c is the length of the side C, small c. It is the length of the arc AB. Now there is a basic relationship among the 3 surface angles of a spherical triangle. In plane trigonometry, the sum of the 3 angles in any triangle is equal to 180 degrees, and this is stated as the triangle sum theorem. In a spherical triangle, the sum of the 3 surface angles can be more than 180 degrees, and that's another basic difference between the spherical triangle and the plane triangle. If we add alpha, angle beta, and angle gamma, the 3 angles at vertices A, B, C, alpha, Alpha is the angle at vertex A. Alpha is the angle formed by the intersection of the arcs AC and the arc AB. Plus angle beta. Angle beta is the angle at vertex B. It is the angle formed by the arcs. BC and AB of two great circles. If we add to this sum angle gamma, gamma is the angle at vertex C. It is the angle formed by the intersection of this arc BC and the arc AC, and these arcs are arcs of two great circles of the sphere. The sum of these three surface angles can be greater than 180 degrees. Unlike a plane trigonometry, the sum of the three angles is always 180 degrees. But the sum cannot be more than 540 degrees. So this is one basic property of the spherical triangle. The sum of the three surface angles, the angles formed by the intersection of two arcs of two great circles, can be more than 180 degrees, but less than 540 degrees. If we subtract 180 degrees from the sum of these three surface angles, alpha plus beta plus gamma, from the sum we subtract 180 degrees. The difference is denoted by a small e, capital letter E. If you subtract 180 degrees from the sum of the three surface angles of a spherical triangle, the difference is denoted by capital letter E, and it is called the spherical excess. Spherical excess is the difference between the sum of the three surface angles of a spherical triangle and 180 degrees. Again, in spherical triangle, the sum of the three surface angles can be more than 180 degrees, but less than 540 degrees. Earlier, we said that the measures of the three sides of a spherical triangle are given by the measures of the angles subtended by these arcs at the center of the sphere. So the three sides, denoted by small a, small b, small c, of a spherical triangle are also known as central angles. Therefore, a spherical triangle has 6 parts. It consists of 3 surface angles and 3 central angles. The surface angles are angles on the surface of the sphere, and they are formed by the intersection of 2 arcs of 2 great circles, while the central angles are the sides of the spherical triangle, and their measures are given by the angles subtended by the arcs by the side at the center of the sphere, for which reason these sides are known as central angles. Spherical trigonometry originated in the Islamic caliphates. A caliphate is an Islamic state under the leadership of a caliph. And a caliph is said to be a successor of the prophet, Islamic prophet Muhammad, who is also the leader of the entire Muslim community. So spherical trigonometry originated in the Islamic caliphates of the Middle East, North Africa, and Spain during the 8th century and to 14th century. And the basic problem they were solving them was finding the direction going to Mecca. The developments in spherical trigonometry lead to improvements in the art of navigation, improvements in geographic map making, in stellar map making, and in the positions of sunrise and sunset. In navigation, the Earth is considered as a sphere. And a basic problem encountered in navigation is finding the distance between two places on Earth. And these two places are represented by 2 points on the surface of the sphere, such as point A and point C. And from this diagram, you can see that the distance between these points A and C is the length of this side of the spherical triangle. And the length of this side is actually the length of this arc through the points A and C. Or the length of the arc through the vertices A and C of the spherical triangle. And we said earlier that the length of this side B or the length of this arc AC is given by the measure of the angle subtended by this arc at the center of the sphere. Here in the diagram, the center of the sphere is denoted by point 0. And the central angle subtended by this arc AC is the angle B. In circle in the plane, the length of arc is easier to find. Here, this is the center of the circle, and R is the radius of the circle. The central angle, the angle with vertex at the center of the circle, subtended by this arc A, is given by the angle theta. And the length of this arc A is a part of the circumference of this circle with radius R. Hence, the length of arc A, denoted by L sub A, L for length, or denoted by this notation, the length of arc A is equal to the circumference of the circle. The circumference of the circle with radius R is given by 2 pi R. Multiply by the central angle theta. It's a central angle because its vertex is at the center of the circle, and it is the angle subtended by the arc at the center of the circle, and divide by 360 degrees. This arc length can also be found by use of this formula. The radius of the circle multiply by pi and divide by 180 degrees. Suppose this is a unit circle, which means that the radius of this circle is 1 unit. And suppose that the central angle theta subtended by the arc A at the center of the circle is 60 degrees. We find the length of arc A by use of the first formula. L sub A equals 2 pi multiplied by R. The radius is 1, so this is a unit circle. Thus, multiplied by the central angle theta, which we take as 60 degrees, and divide by 360 degrees. And 60 and 360 are divisible by 60. So I divide 60 by 60 is 1. 360 divided by 60 is 6. and you have 2 pi over 6. In lowest term, that's pi over 3. So the length of this arc that subtends an angle, central angle of 60 degrees at the center of the circle of radius 1 unit is pi over 3 units. Using the second formula for finding the length of arc, we have length of arc A is equal to pi. The radius is 1 unit, it's a unit circle. Multiply, divide by 180 degrees. And there should be an angle theta here. The second formula for the length of arc is pi times the radius of the circle times the central angle subtended by the arc at the center of the circle, divide by 180 degrees. By using the second formula, the length of arc is pi. Our radius is 1 unit because it is a unit circle. Multiply by the central angle theta, 60 degrees. And divide by 180 degrees. 60 and 180 are divisible by 60. So we divide 60 by 61. Multiply by 1, multiply by pi is pi. Divide by 180, divide by 60 is 3. And we get the same results. Pi over 3 units is the length of arc A that subtends an angle of 60 degrees at the center of the circle with radius 1. This is how we find the length of arc A on a circle of radius r. In spherical trigonometry, the length of arc B, or the length of this arc AC, is the measure of the angle subtended by this arc AC at the center of the sphere, here at point 0. And it is in finding this central angle B, the length of this arc AC, that we will apply the law of sines and cosines for spherical triangles. If one of the angles of a spherical triangle is 90 degrees, then we have a right spherical triangle. As in plane triangle, if one of the angles is 90 degrees, fixed at 90 degrees, then the triangle is a right triangle. In the next lesson, we will start with solution of right triangles, solution of right spherical triangles, where one of the angles of the spherical triangle is equal to 90 degrees. If you have question about the lesson today, you ask your question in the comments below. And do not forget to subscribe to my YouTube channel, Art Kalison. Thank you.